Hello everyone, welcome back to my YouTube channel. In this video, let us solve a problem on parallel RLC circuit to find unknown resistor which is connected in series to capacitance. So here they are given the value of resistor connected in series to inductor, that is RL value they are given, that is RL value is 30 ohm, RL they are given, and they are given XL, and they are given RC and XC. So that first you see in the left side, that is this branch. Here resistance is 30 ohm, inductive reactance is plus J12. So that impedance you are writing that as a 30 plus J12 because it is connected in series. Similarly, branch 2, RC is unknown resistor connected in series to capacitive reactance, and capacitive reactance is minus J12.5. Therefore, these two are connected in series. RC plus or minus, that is plus into minus, that is minus J12.5. So you're getting impedances. Now you write admittance, that is B, susceptance. That is nothing but reciprocal of your impedance. That is the imaginary part of total admittance, that will be 0. This is the condition for resonance in parallel circuit. So that at resonance, net susceptance equals to 0. That is nothing but imaginary part of total admittance equals to 0. Therefore, of this is branch 1. For that, your admittance, you are writing that as a y1, which is given by inverse of z1. That is nothing but 1 by z1. Therefore, you are writing 1 divided by 30 plus j12. You do partial, you just multiply the conjugates into here. That is nothing but you just multiply here 30 minus j12 divided by 30 minus j12. Therefore, in a numerator, it will get 30 minus j12. In denominator, a plus ib into a minus ib is nothing but a square plus b square, where a is 30, b is 12, so that 30 square plus 12 square. So just reducing this, 30 minus j12 as it is, 30 square is 900, 12 square is 144. Therefore, 30 minus j12 divided by, if you add these two, you will get 1044. So now we are doing separately, you are writing that is 30 divided by 1044 minus j into 12 divided by 1044. That is nothing but 30 divided by 1044 is 0.0287 minus j into 12 divided by 1044 is nothing but 0.0115 susceptance, or else you can write more. Okay. Similarly, for second branch, y2, you are writing that as a 1 divided by z2. Y2 is nothing but 1 divided by z2, whereas z2 is nothing but rc minus j12.5 multiply and divided by complex conjugate of this, that is rc plus j12.5 divided by rc plus j12.5. So in a denominator, it becomes RC square plus 12.5 square. In a numerator, you can get RC plus J 12.5. You are separating writing now. This you can read it as RC divided by RC square plus 156.25 plus J into 12.5 divided by RC square plus 156.25. I hope you are getting. These are the two equations of y1 and y2. So now condition. Resonant condition is imaginary part equals to 0. That is imaginary part of y1 and imaginary part of y2, that will be equals to 0. Whereas imaginary part of y1 is minus j 0.0155, sorry, 0115. And here for y2 it is 12.5 divided by rc square plus 156.25. Therefore, you are writing here minus 0.0115, that is the imaginary part of y1, and imaginary part of y2 is 12.5 divided by rc square plus 156.25 equals to 0. So now we are solving this. You are sending this minus 0.0115 to the right side, that becomes plus. You can directly use calculator or else you can solve here. Then you are interchanging these two, it becomes RC square plus 156.25 equals 12.5 divided by 0.0115. Then you simplify this, you get 1086.96. You send 156.25 into the right side, it becomes minus, and total you'll get RC square equals 930.71. We want RC so that square root on both sides, you'll get RC equals 30.5. This is the answer. Similarly, next one is C. Derive the expression for resonant frequency and quality factor of parallel RLC circuit. So you can refer, I'll show this link later. So you can see here a series RLC circuit. I'll draw here. It is having a resistor R, inductor L, capacitor C, which is connected across the voltage source V, and it is having 15 ohm of resistor, 40 millihenry of inductor, 40 microfarad of capacitor, and the applied voltage is 75 volts. They are asking you to find resonant frequency, that is F naught or omega naught, and current at resonance, that is nothing but I naught at Z equals R, and you need to find voltage drop across R, that is VR, VL, VC. These all you need to find. So given you already know. So angular frequency, either you can use F naught equals, sorry. Here either you can use F naught equals 1 divided by 2 pi square root of LC if you want to get F naught in terms of hertz, or else if you want to get in terms of radian per second, omega naught equals 1 by square root of L into C. You know the value of L, you know the value of C. You are just substituting 1 divided by L is 0.04, that is nothing but 40 millihenry into 40 microfarad. So you'll get omega naught as 793.7 radian per second. So next you calculate reactances, means that you are proving the at resonance Z equals R and XL equals XC. So XL is given by omega naught into L. By substituting that, you'll get XL as 31.75, and XC is 1 divided by square root 1 divided by omega naught into C. If you are substituting that, you'll get XC equals 31.75. So that this is your resonant condition. Therefore, for series RLC circuit at resonance Z equals R, so that impedance value is 15 ohm. Why you want impedance? To calculate current, because current is given by V divided by Z, where Z equals R, so that current at resonance is V divided by R. V you already know 75, R is 15. We'll get current as a 5 amperes. So current at resonance finished. Next, voltage across R is given by I into R. I you know, R you know. You'll get 75 volts. Voltage across inductor is given by plus J I into XL. So you know the value of I and you know the value of XL. You substitute, you'll get plus J 158.75 volts. Similarly, VC is minus J I into XC, that is minus J 5 into 31.75. You'll get 158.75 volts. This is about your series resonant circuit. I hope you are getting this. If you have any doubts, feel free to write in the comment box. If you like this video, do subscribe and share maximum. Thank you. Have a nice day.